Welcome. This video is going to take a look at another type of covalent bond, something that's called a dative or coordinate covalent bond. And before we get into that, I would just want to review the types of formulas we've been using. When we refer to the idea of a molecular formula, that is the shortest, most concise way to write a formula such as pH3. It also gives you the least amount of information. It simply tells you that there's a phosphorus in the center of the atom with 3 hydrogens attached to it. A Lewis structure, on the other hand, gives us quite a bit more information because now the Lewis structure actually draws a two-dimensional representation of the atoms and showing the bonds between them. So when I look at this, I can see that there is a phosphorus atom, and my graphics are a little bit tough to decipher here because I have to use the computer, but you can see there's a lone pair up here, and then there's a bonding pair here, a bonding pair here, and a bonding pair here. There's also something called the structural formula, and we're not going to be using structural formulas right now because they show the bonds, but you'll see your book does this sometimes. So it shows the bonding pair, and that's a bonding pair there. But it doesn't bother showing the lone pair. And the lone pair is important to us, and you'll see why a little later as we start discussing shapes. So a dative bond, or a coordinate covalent bond, is when one atom donates both electrons to the covalent bond. Okay, it's called a coordinate covalent bond or a dative bond. Either one, you'll see both terms used. Your book happens to use the term coordinate covalent bond. But so far, all of our covalent bonds that we've been drawing, each atom is donating an electron. And in fact, in earlier science classes, you were probably told each atom has to donate an electron. But that's not true. If it makes both atoms stable, then one atom will go ahead and donate both electrons. And dative bonds behave just like any other covalent bonds. So it's not like we have to draw it differently or signify it differently, but it means we have to think a little bit different about our Lewis structures because they're going to get a little bit messy to draw. So we're going to look at a new system to use that will work whether it's a dative bond or just a regular old covalent bond. This method will work for any covalent bond. And in fact, it works especially well with multiple covalent bonds. So let's take a look at carbon monoxide and see what's wrong with our old method of thinking about this. So if I think about carbon, it has 4 unpaired electrons, so it's looking to form 4 bonds. So I'm going to draw the line showing it wants 4 bonds. Oxygen, on the other hand, only needs 2 bonds, and let me switch that up and make these blue so we can tell who's who. And it is ready to form 2 bonds. So normally we'd think of carbon and oxygen forming a double bond. And oxygen is good now. It's shared the 2 electrons it needs to. It's got its lone pair. But carbon's got a problem here because these 2 single electrons can't bond with each other. A bond has to be between 2 atoms. But what can happen is these 2 electrons can pair up. And then I've got my double bond here, and I've still got my lone pair here, which still doesn't help anything because carbon's still missing its 4th pair. So what happens is oxygen actually donates this pair to come in and form a triple bond because that doesn't make oxygen any less stable to move that pair into the shared region, move it into a pi bond, and it makes carbon a whole lot more stable. And when carbon's more stable, that's good for oxygen because then carbon will hang around in this bonding arrangement. So that's a little bit complicated to figure out, and that's a fairly straightforward one. So what's an easier method to determine this? And we really don't need to know if it's a dative bond or not, at least for what we're doing. So a simpler method, I think, is to use this strategy here. What I like to do is I add up the total number of valence electrons in the molecule. So I look at each atom and see how many valence electrons each one has. Then I draw the central atom. It should be the first element, unless of course it's hydrogen, then look at the second element. I attach all the other atoms to the central element, to the central atom, using a single bond. Then I fill in the lone pairs on all the atoms and see that each atom has a full octet. Count up that total number of electrons that I use to draw the molecule, And now I compare that to the number of electrons that I calculated I had back in step 1 and look to see if I need any double or triple bonds. And let me just shrink this up here. Come on, you can shrink. Let me shrink this up here and redraw my carbon monoxide following my 5 steps here. So if I have carbon monoxide, CO, I have 4 electrons, 4 valence electrons from carbon and 6 from oxygen for a total of 10 electrons. If I draw the central atom and attach the other atoms with single bonds, I end up with just CO. Then it says fill in the lone pairs on all the atoms so each atom has a full octet. That means I would have to put 3 pair on each atom. You're saying, wait, you don't have enough. It's okay, it's going to work out. So now I count up how many electrons I used to do that. 2, 4, 6, 8, 10, 12, 14 electrons. And you're right, I used more than I had. If I subtract, I've used an extra 4 electrons. Obviously I can't just create electrons. So if you've used more electrons than you have, you need to add a double or a triple bond. And it says 1 bond will save 2 electrons. So since I have 4 electrons that I need to use up, that I need to save, I need to form 2 more bonds. So I'm going to go back and revise my diagram. I had 1 bond there. I need to add 2 more. So now if I put a triple bond in, I'm going to go back to step 2 here. I'm going to fill in the lone pair each one needs. Now if I count up, I have 2, 4, 6, 8, 10 electrons total, which matches the 10 electrons I actually have from carbon and oxygen. So this must be a correct diagram for carbon monoxide. And that's quite a bit easier than the method I used originally. Here's another example. I used NH4 with a +1. This is a polyatomic ion. It's one of the few that has a positive charge. And remember, a plus charge means it's lost an electron. A -1 means it's gained an electron. So NH4, nitrogen would have 5 electrons. The 4 hydrogens each have 1 electron. And then the +1 means I've lost an electron. So when I add this up, 5 and 4 is 9 minus 1. I actually only have 8 electrons. So I go ahead and put N in the center. I attach each hydrogen with a single bond. I add any lone pair I need. Well, hydrogen only needs 2, just needs the 1 bond. Nitrogen's got 4 pair, so I don't need any lone pairs, and I'm done. Now, because it's got the +1 there, it would be most correct to bracket this whole thing and put a plus sign here or a +1 sign to show that an electron has been dumped somewhere. So that would be my electron structure for it. That's much simpler than thinking about nitrogen with its 5 valence electrons and trying to figure out how to get 4 hydrogens on there, okay? That's just going to mess with your head. So now after spending all that time trying to figure out valence electrons and having a picture of dot diagrams, it's better to forget that and see if you can use this new method. So I've got a couple try-its for you. I'd encourage you to pause on each one and see if you can do it yourself. You maybe need to refer back to the steps, and that's okay. But I'm going to go ahead and start on POCl3. So if I look up phosphorus, it's got 5 electrons. Oxygen has 6. And I have 3 chlorine with 7 each. So I got 5 and 6 is 11 plus 21. This is 32 electrons total. The P is first, so it goes in the center. I attach an oxygen with a single bond. And then I have 3 chlorines to attach with single bonds. And now I need to fill in lone pairs. So each chlorine gets its 3 lone pair. And then oxygen also gets 3 lone pair. And I know some of you are going, wait a minute, it only had 6 electrons. It's okay. Somebody donated the extra electron for oxygen. We don't have to worry about that. But when I count up, what I have to worry about is I only have 32 electrons to share among all 5 of these, and I can share them any way I want. And when I count up here, I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's what I've used, is 32 electrons. So this structure is correct for POCl3. One more for you to try, H3O plus 1. Again, pause and try it yourself. I've got 3 hydrogen with 1 electron each. I've got oxygen with 6, and then there's been 1 electron lost. So we're looking at a total of 8 electrons here. H can't be in the center because it can only form 1 bond, so oxygen's the center atom with 3 hydrogens attached. Oxygen needs 1 lone pair for a total of 4 pairs of electrons. Hydrogen's good. I should bracket this and indicate it's lost an electron. And now when I count up, I've got 2, 4, 6, 8 electrons. So again, my structure is good.